Welcome back to the deep dive. Today we're jumping into something really fundamental, something that totally changes how you see the universe.
We're talking quantum mechanics.
Exactly. It messes with common sense. We've got some questions and answers here, kind of laying out the basics, and we're going to try and unpack them.
That's the plan. Think of it like looking under the hood. We'll see why the old physics, classical physics, just wasn't cutting it anymore at the tiny scales.
Right.
And what weird new ideas came in, and importantly, how they actually connect to things we can see and use. We're sort of getting to the core concepts.
Okay, let's dive right in then. We all learned about Newton, right? Apples falling, planets orbiting. That's classical physics. Works great for, everyday objects.
Absolutely. Billiard balls, planets, that sort of thing.
But you said it breaks down completely when you get really small, like atoms, electrons.
Rough.
Why? What was it missing?
Well, classical physics pictures a smooth, predictable world. Energy can be anything. Position and speed can be known precisely. Everything's continuous. But experiments, starting around the turn of the 20th century, they just kept showing results that didn't fit that picture at all.
Like what? Give us an example.
Okay, a big one was black body radiation, how hot things glow. Classical physics predicted this thing called the ultraviolet catastrophe.
Sounds bad.
It was. It predicted infinite energy pouring out at high frequencies, which obviously doesn't happen. Max Planck fixed it, but he had to make a really radical suggestion.
Which was?
He said energy isn't continuous. It comes in chunks, little packets, quanta. The energy of light is tied to its frequency, E equals h times nu, where h is this tiny nu constant, Planck's constant.
So energy is quantized, like steps instead of a ramp.
Exactly like steps. You can only be on certain energy levels. And then there was the photoelectric effect.
Right. Einstein explained that one.
He did. Shine light on metal, electrons pop off. Classically, brighter light should mean faster electrons, more energy.
Makes sense.
But nope. Experiments showed electron energy depended only on the light's color, its frequency, not brightness. Einstein said light itself acts like particles, photons, each carrying one of Planck's energy quanta.
Wow. Okay, so energy comes in packets, and light acts like particles sometimes? That's already weird.
It is. And atoms themselves were a puzzle. A classical electron orbiting a nucleus should radiate energy away constantly and spiral inwards. Poof, no more atoms.
But atoms are stable, mostly.
Exactly. Niels Bohr proposed electrons could only be in specific orbits, specific energy levels, and they don't radiate when they're in those stable orbits. More quantization.
Okay, so experiments forced this new view. Quantized energy, particle-like light, stable atoms needing special rules. And this led to maybe the weirdest idea of all, wave-particle duality.
That's the cornerstone, really.
Yeah.
Louis de Broglie had this brilliant thought. If waves like light can act like particles, maybe particles like electrons can act like waves.
Seriously, not an electron has a wave.
He proposed every particle has a wavelength, lambda equals h divided by p. It's momentum. More momentum, shorter wavelength.
How on earth could you test that?
Davisson-Germer did, around the 1920s. They fired electrons at a nickel crystal. If electrons were just tiny balls, they'd scatter randomly, maybe.
But they didn't.
No, they saw an interference pattern, just like waves do when they overlap constructive and destructive interference, ripples adding up and canceling out.
Whoa, direct proof.
Direct proof that electrons have wave-like properties. Matter isn't just particles or waves, it's both somehow, depending on how you look.
So how do you describe something that's both? That sounds impossible. Is that where the wave function comes in?
That's exactly where it comes in. If particles act like waves, you need a wave equation to describe them. Enter the wave function, usually written as 80 Karazu, I psi.
Psi. Yeah.
In quantum mechanics, instead of definite positions and speeds, a particle's state is described by this phacos. And the rules involve operators replacing classical numbers, but the key is this math captures the wave nature.
But what does it do? Physically?
Yeah.
Is it like a little wave rippling through space?
That's the million-dollar question. And the answer is sort of no. The wave function itself isn't directly physical. You can't, measure its height like a water wave.
So what good is it?
Its meaning comes from its magnitude squared. Check to 2. This is Born's rule. It tells you the probability density of finding the particle at a certain place at a certain time.
Probability. Okay, so it's not saying where the particle is, but where it's likely to be.
Exactly. Where check 2 is large, high probability of finding it there. Where it's small, low probability, it's fundamentally probabilistic.
And all those probabilities have to add up.
They have to add up to 1. You have to find the particle somewhere if you look everywhere. That's called normalization. And can be complex, have imaginary parts, which is crucial for describing interference.
Right, the wave interference needed that phase information. Okay, so it's probabilistic, described by Czech. What happens when particles aren't free, but are, say, trapped?
Good question. That leads us to potential wells. Imagine a dip in the energy landscape, a region where the particle has lower potential energy. It can get trapped there.
Like a ball rolling into a ditch.
Sort of. A simple model is the rectangular potential well. Think of an electron stuck in a tiny wire.
What happens then, quantum mechanically?
If the walls are infinitely high, an infinite well, the particle is completely trapped. Solving the math, the Schrödinger equation shows its energy is quantized again. Only certain specific energies are allowed.
Like the steps again?
Like steps again. And the energy levels depend on the size of the box. L, smaller box, higher energy steps. The wave function inside looks like standing waves on a string. But the really weird stuff happens with finite wells, where the walls aren't infinitely high.
Okay.
Even if the particle's energy is less than the height of the wall, classically, it's stuck inside. The wave function doesn't just stop at the wall, it leaks out.
Leaks out?
It decays exponentially into the barrier region. It's not zero immediately outside the well.
Wait, so there's a chance, a non-zero probability, of finding the particle outside the well, even though it doesn't have enough energy to climb the wall.
Precisely. That's quantum tunneling. It's maybe the most famous non-classical effect. The particle, because of its wave nature, can literally tunnel through an energy barrier it shouldn't be able to overcome.
Like it goes through a wall. That's mind-bending. Does that actually happen?
Oh, absolutely. It's not just theory. The probability, called the transmission coefficient T, depends on the barrier, thickness, and height, and the particle's energy. Thicker barrier, lower chance. Higher barrier, lower chance. But it's never zero for finite barriers.
And this tunneling? It's useful.
Hugely useful. It's essential for nuclear fusion in stars. Protons tunnel through their mutual repulsion. Alpha decay and radioactivity is tunneling. Modern electronics depend on it, understanding electron behavior in semiconductors.
Wow.
Superconductors use Josephson junctions, which rely on tunneling. And there's an amazing imaging technique based on it, the scanning tunneling microscope.
STM.
STM. How does tunneling let you see things?
You take an incredibly sharp metal tip, bring it nanometers away from a surface, apply a small voltage. The gap, the vacuum or air, is a potential barrier.
Electrons can quantum tunnel across that gap, from the tip to the surface or vice versa, and the amount of current that tunnels is extremely sensitive to the gap distance. Tiny changes in distance make huge changes in current.
Ah, so you scan the tip.
Exactly. You scan the tip across the surface, and you either measure the change in current at a fixed height, or you move the tip up and down to keep the current constant. Either way, you build up a map of the surface, atom by atom.
You can see individual atoms using tunneling. That's incredible.
It is a direct application of pure quantum weirdness.
Okay, another fundamental system you hear about is the harmonic oscillator, like a quantum spring.
That's a great analogy. It models anything that oscillates around an equilibrium point, atoms vibrating in a molecule, for instance. The potential energy looks like a parabola.
And solving the Schrödinger equation for that, more quantum rules.
Yep. First, energy is quantized again. N equals h bar omega times n plus a half, where n is 0, 1, 2. Omega relates to the spring's stiffness.
So quantized steps, are they spaced like the particle in a box?
No, interestingly, they're equally spaced, like a perfect ladder.
Right.
Each step up adds the same amount of energy, h bar omega.
Equal spacing. Okay. Anything else?
The other really strange thing is the lowest energy state, n0. The energy isn't zero, it's E0 equals 1/2 h bar omega.
Half h bar omega. It can't be perfectly still.
Never. That's the 0-point energy. Even at absolute zero temperature, a quantum oscillator still jiggles with this minimum energy. It's a consequence of the uncertainty principle, fundamentally. It's hugely important: molecular vibrations, lasers, quantum fields.
0-point energy. Wild. Okay, so we've seen single particles in wells on springs. What about multiple particles, like interacting?
Right, like two particles forming a molecule or an electron and proton in an atom. The description gets more complex, obviously. You have kinetic energy for both, plus potential energy from their interaction.
How do you handle that?
A standard trick is to switch coordinates. Instead of tracking each particle individually, you track the motion of their combined center of mass and the relative motion between them.
Why do that?
It separates things nicely. The center of mass motion is usually simple, like the whole system just moving through space. The interesting quantum stuff, vibrations, rotations, happens in the relative motion. You use something called the reduced mass, mu, to describe that relative part. And when you describe that relative motion, especially if the force depends only on distance, like electric attraction, angular momentum becomes really important.
Angular momentum, like spinning. Is that quantized too?
Oh yeah, big time. Just like energy, angular momentum in quantum mechanics comes in discrete chunks. Both its total magnitude and its direction along one axis are quantized.
Seriously?
Yep. We talk about orbital angular momentum from motion and spin, which is an intrinsic angular momentum particles just have. These quantum numbers, L and M and L for orbital, says for spin, dictate the allowed values. It's why electron orbitals have specific shapes, why molecules have specific rotational energies.
This connects to another thing. Operators. And whether they commute. You mentioned position and momentum earlier couldn't be known together.
Exactly. In quantum mechanics, measurable things, position, momentum, energy, angular momentum, are represented by mathematical operators. Think of them as instructions. Measure the position or measure the momentum. They act on the wave function. Now, the order you apply these operators can matter. If two operators, say A hat and B hat, commute, meaning A hat, then B hat gives the same result as B hat, then A hat, then you can measure both quantities A and B precisely at the same time. They're compatible.
Like energy and angular momentum sometimes.
For certain potentials, yes. But if they don't commute, if A hat, B hat is not zero, then the quantities are incompatible. You can't know both perfectly simultaneously.
And position and momentum don't commute.
They famously don't. The commutator X hat, P hat, is I times H bar. It's not zero. This mathematical fact is the deep reason behind the Heisenberg uncertainty principle.
So the math itself forbids perfect knowledge. It's not just bad measuring tools.
It's fundamental. The uncertainty principle, x times greater than or equal to h bar over 2, is a direct consequence of that non-commutation. The more you pin down position, small x, the fuzzier momentum gets, large up, and vice versa. It applies to other pairs too, like energy and time. A times 8 is also limited by h bar over 2. We can see this in action with simple models, like the rigid rotator. Imagine two atoms stuck together at a fixed distance, spinning.
Like a tiny dumbbell.
Exactly. Its rotational energy levels are quantized, depending on jj plus 1, where j is the rotational quantum number, and the molecule's moment of inertia, I.
And that moment of inertia depends on the masses and the distance between them.
Right, I equals mu times r squared, where mu is the reduced mass and r is the bond length. So if you measure the energy needed to jump between rotational levels, you can do that with spectroscopy. Seeing what light frequencies it absorbs, you can find I.
And if you know the masses.
You can calculate R, the bond length. For nitrogen, N2, the lowest rotational transition energy, is about 2.48 times 10 to the 4 eV. You plug that into the EJ formula, calculate mu for nitrogen, and solve for R. It comes out around 1.09 angstroms. A direct quantum mechanical calculation of molecular structure.
That's really cool, using quantum rules to measure molecules. Okay, let's zoom out a bit. The core equation underlying all this.
Yeah.
That's the Schrödinger equation, right?
That's the one. It's the master equation. It tells you how the wave function evolves in time, or in its time-independent form, what the allowed stationary states and energies are for a given system. H hat equals EF. H hat is the Hamiltonian, the total energy operator. You plug in the potential energy for your system, like the Coulomb potential for the hydrogen atom, the electric attraction, and solve the equation.
And for hydrogen, that gives...
It gives the exact energy levels. N equals 13.6 eV divided by n squared with n1, 2, 3. These perfectly match the observed spectrum of hydrogen light. And it gives the wave functions, the orbitals, those probability clouds, like SPD orbitals showing where the electron is likely to be found. Not orbits, but probability distributions with shapes dictated by angular momentum quantization.
And the size is related to the Bohr radius.
Yes, the Bohr radius emerges as the characteristic size of the ground state electron cloud, about half an angstrom.
So Schrödinger gives us the probabilities.
Yeah.
And you said earlier, probability is conserved.
Absolutely. Total probability must always be 1. The math of the Schrödinger equation guarantees this. There's a continuity equation, like in fluid dynamics, that relates changes in probability density to a probability current. Probability flows around. It doesn't just appear or disappear.
Okay. And if we measure something, we get one specific result, but the theory is probabilistic. How do we connect those?
Through the expectation value. If you measure, say, position on a system in state, you'll get some value. If you prepare many identical systems in state and measure position on all of them, the average of all your results will be the expectation value.
The average outcome.
Exactly.
Yeah.
Calculated by sandwiching the operator between muck-in and integrating, it's the probability weighted average of all possible outcomes.
Got it. We talked uncertainty principle. What about superposition? That sounds important too.
Oh, it's fundamental. It's the idea that before you measure, a quantum system can be in a combination of multiple states at the same time. An electron could be in a superposition of spin up and spin down, or in two places at once.
Until you measure it.
Until you measure it. Then the superposition collapses into one definite state. This ability to exist in multiple states simultaneously is what makes quantum computers potentially so powerful, using qubits that can be 0, 1, or both at once.
Okay, wow. We've covered a lot. Classical physics failing, wave-particle duality and probability, tunneling, quantization in Wells and oscillators, angular momentum operators, uncertainty, Schrödinger, hydrogen, superposition. We even mentioned some specific calculations. Could we recap those quickly, just the numbers?
Sure, they help make it concrete. The de Broglie wavelength for a 10-keV electron was about 0.124 nanometers. Tiny, but definitely wave-like, hence electron microscopes.
Right.
The uncertainty principle calculation linked spectral line width to the lifetime of an excited state. A typical result might be around 10-13 seconds, very short. Normalizing a wave function involved finding a constant to make the total probability equal 1. For the particle in a box, the average position was the middle, L2, but the RMS position gave a measure of the spread, how much uncertainty there was in its location, and the nitrogen molecule calculation, using the measured rotational energy from spectroscopy and the rigid rotator model to find the bond length, about 1.09 angstroms.
It's amazing how these abstract ideas lead to precise, testable numbers about the real world.
It really is the power and, honestly, the beauty of quantum mechanics. It gives us this incredibly accurate description of the microworld.
Well, this deep dive has certainly shown that the quantum world is definitely not intuitive. It's strange, probabilistic, limited by uncertainty, but also incredibly powerful in explaining how things work at the smallest scales.
And it's the foundation for so much modern tech, from lasers to semiconductors to medical imaging, and we're still exploring its implications.
So as you, our listener, think about all this, here's something to chew on. If the fundamental reality described by quantum mechanics is probabilistic, if particles only gain definite properties when we measure them, what does that really mean for our concept of reality? Does the observer play a necessary role in creating the world we see?
That's the kind of question that keeps the debate going. What is the nature of measurement? What is reality at that level?
Deep questions indeed. Thank you for joining us on this quantum journey. We hope it sparked some curiosity. Keep questioning, keep exploring.